Okay, hi. Welcome to the Intermountain Weatherization Training Center. My name is Wade Thompson. I'm the lead instructor here. And if you're watching this DVD, there's a high probability that you'll be taking your BPI field test here at our training center. The purpose of this DVD is to walk you through a BPI field exam so you know what to expect before you get here. I highly recommend that you take notes, that you pay attention, and that you watch this DVD as many times as you can before you get to your field exam. The BPI field exam is an open book test. That means that you can have any materials you want with you. So some of the materials that you can have with you and that you may want to have with you are things like this. This is a quick reference guide for the blower door. The blower door is one of the diagnostic tools you'll be using. There's a lot of steps and a lot of things to remember in setting one up and using it. You may forget some of those steps. So if you have this reference material, you can refer to it during the test, and that's perfectly fine with BPI. A couple of other things are these quick reference cards. This one, for example, has all the various BPI standards on it that you'll need to know for the testing. During the course of the test, the proctor may ask you questions about the standards, and you'll need to be able to answer those. There's a lot of information here. It's extremely hard to memorize it all. So have these standards with you so that you can look the questions up. Again, quick reference cards for setting up your CAS zone testing and your blower door. Just so if you forget a step or you forget what's next, you can refer to your quick reference cards. I'll give you a little reminder. The other thing is the BPI standards. You can download all of this from the BPI website. This has all of the standards you'll need to know for the field test that you're taking. The only thing you can't have with you during your BPI field exam is your cell phone, so leave that home. The other thing you need to know about the BPI exam is it's broken down into modules, depending on which test you're going to take. You'll either be taking the building analyst or the envelope professional. For each one of those designations, there's different modules. For example, here, the front page of this shows one module, or the first module is fuel delivery. The fuel delivery module is only required if you're taking the building analyst exam. If you're taking the envelope professional, you don't need to worry about fuel delivery. These are all the modules in which you will need to show proficiency in order to pass the BPI exam. The next one on this page is combustion safety. The combustion safety module is required for both the building analyst and the envelope professional. Through the course of this DVD, I will walk you through each of these modules contained in here so that you'll get to see before you test exactly what you need to be proficient at in each of these modules in order to pass your BPI field exam. The other thing you'll want to have with you is a personal CO detector. This just clips onto your shirt or your belt, and it monitors the CO levels the whole time you're testing. If you don't have a personal CO detector, we will probably have some available for you to borrow, or you can take a piece of paper with a sticky note or a piece of tape and write CO detector on it and stick it on your shirt. It's important that you let the proctor know, I have my personal CO detector, whether it's a real one or the one stuck on your shirt. Let them know that you have it and that you'll be monitoring the CO levels during the entire time of the test. That just shows the proctor and BPI that you understand the importance of safety and monitoring carbon monoxide levels the whole time you're testing. Finally, your BPI exam will be filmed. BPI requires that we film all exams to maintain the integrity of the testing. So some people get camera shy or real nervous. Your proctor's going to have a camera, just ignore it, pretend it's not there, go on like it's just a normal test, and you'll do just fine. Okay, we're going to go ahead and I'm going to take you through each of these modules. We're going to start with the fuel delivery module first. Another thing you need to be aware of on the BPI field test is in each of these modules there are going to be components that are just not applicable to this house. For example, in the fuel delivery module, it asks some questions about propane and oil. Well, this house has either a propane tank or an oil tank or any appliances that run off of either of those fuels. So if you find something in a module that's not applicable to the house that you're working in, or this house in particular, just skip over it and don't worry about it. The proctor will mark it as NA or not applicable. Okay, the first module I'm going to take you through on the DVD is the fuel delivery module. If you're taking the building analyst exam, this is a module that you'll need to show proficiency at. Okay, we're going to go ahead and start outside at the gas meter. So I'm going to come over here to our gas meter on the house. I'm going to take my combustible gas analyzer or detector and I'm going to turn it on. It takes just a minute for this to warm up, so we're going to let it warm up until it starts clicking. Once it starts clicking, you turn it up until it squeals and then back it off until it's just clicking. BPI standards say that you'll check the gas line at a rate of 1 inch per second. So I'm going to start here at the gas meter and I'm just going to go around this gas line, paying special attention to all of the joints. Again, at a rate of 1 inch per second. And I'm going to go ahead and check all of the gas lines that are exposed outside and around this gas meter. Okay, we completed our gas leak test outside at the gas meter. Now we're inside in the mechanical room. Again, you want to check all accessible gas piping. So in here in the mechanical room, we're going to go ahead and check these gas lines. Again, the BPI standard is check it at a rate of 1 inch per second. So I'm just going to go ahead and I'm going to run my gas sniffer or gas detector down this gas line. If your detector picks up a leak, you're going to hear a noise like that. If you pick up a leak, the proctor may ask you a question. What would you do to verify that leak? What I would do to verify this leak once my detector picks it up is I'd use a solution of soap and water and put it on there. It will bubble up, and that's the best way to verify a leak once you've detected it with the detector. You'll go ahead and continue to check the rest of this gas line. Another thing you want to make sure of is gas flexes. You need to check all gas flexes, make sure that there's no corrosion, no kinks, no rips, tears, or holes or anything like that in them. And of course, check them with your combustible gas leak detector. The next area we're going to want to check is the gas range. So what we're going to do is we're going to go ahead and pull this gas range out away from the wall. It only needs to come out about 6 or 8 inches. We're going to get behind it where we can access the gas line. And again, the BPI standard is check it at a rate of 1 inch per second. And I'm just going to work my way across this gas line back here, make sure there's no leaks. If I did detect a leak, then I would verify that leak using a solution of soap and water, get it to bubble up. Okay, the next module we're going to talk about is the combustion safety module. This module you'll have to show proficiency at in both the building analyst and the envelope field exam. So it doesn't matter which one you're taking, you're going to have to show proficiency at this module. So the first thing we want to do in the mechanical room is BPI wants to know, can you identify the types of systems in here? So for example, you would point out that this furnace is a 90% or higher efficient furnace. One of the dead giveaways on that is the fact that it has plastic or PVC exhaust and intake. The flue temperatures are low enough that we can use this type of material without melting them. If it was not over 90% efficient, the flue temperatures would be somewhere between 300 and 500 degrees and would easily melt these pipes. Another dead giveaway of a furnace that's over 90% efficient is this condensate drain that comes out of the actual furnace. High efficient furnaces over 90% efficiency produce condensation or water waste. That's another dead giveaway. So those are things you're going to need to be able to point out to the proctor. Along with the fact that this is a sealed combustion chamber. The burners and the combustion process takes place inside of this sealed chamber. That's why the furnace has 2 pipes. One is to exhaust the gases and the other one is to bring air in for combustion to this chamber. Because it's sealed, it can't get its air from the surrounding area, so it's got to come from the outside. A few other things you may want to point out to the proctor is this is the gas valve. This is what controls the flow of gas to the burners. This is an inducer motor. Inside of here is the blower compartment. You can see where the condensate drain continues into the furnace. So these are just a few things that you'll want to point out to the proctor so that they know you understand what type of equipment you're looking at. You'll also want to check the venting system, the exhaust venting system, and make sure that there's nothing wrong with it. There's no disconnected joints. There's no signs of condensation leaking down here, which would mean there's a leak in the pipe somewhere. There's no sags or kinks or anything out of the ordinary on this venting system. Okay. Next, you want to point out a few things on the water heater. One thing that's critically important to know about this water heater is it's what's classified as an orphaned water heater. That means it's the only natural draft appliance tied into this masonry chimney. It's all by itself. There are no other gas appliances tied into this chimney with it. So it's classified as an orphaned water heater, and it's important to know that when we get into our CAS testing in here, and I'll explain that later. You want to inspect the condition of the vent or the flue. Is everything connected? Is anything crushed? Is anything unhooked? Are there gaps, holes, or anything like that in it? Is there any indications that it might be a fire hazard? Is the flue too close to combustible materials or anything like that? Those are all things you need to be able to note and show that you understand and have proficiency in. Also, we have a temperature pressure relief device here. Okay, we need to make sure that it's piped to the ground and that it's functioning properly. We have our gas valve here. We have our gas on and off, or gas cock. So these are things that you need to point out as you're doing your combustion safety test. All right, once you've identified the heating system and the domestic hot water heating system and pointed out some of the major components and checked the venting and safety controls on it, the next thing we're going to do is we're going to set this mechanical room up for what's called a worst case draft test, or also known as a CAZ. A CAZ, C-A-Z, is combustion appliance zone. So our combustion appliances are in this zone. We have to test this zone and make sure that this orphaned water heater is going to properly draft, meaning are the flue gases going to leave the house rather than backdrafting into the home. So there's some testing we do to make sure that this is going to vent properly. So the first thing we're going to do is we're going to set up our DG700, which is a digital manometer, and we're going to test the condition of this CAZ. We need to know, is this CAZ under a negative pressure or a positive pressure? Because it determines how air will move through this system and how this water heater will vent. So the first thing we do is we have our manometer mounted here. And we're going to go ahead and set that manometer up. We have this blue hose here. The first piece of information we want to give our manometer is on the A channel. We need to know what our CAZ, combustion appliance zone, is, which will be sensed on this port. We need to know what its pressure is in relation to the outdoors. So I'm going to reference, so I put my blue hose on the reference port, and I'm going to reference outdoors. I take the other end of the blue hose, and I just throw it out this door. It's important to make sure that this hose is not kinked or that we don't crush it in the door. So just close the door just enough so that you don't kink that off. So we now have our manometer sensing pressure in the CAZ with reference to the outdoors. On channel B, we have to set up another hose. We take the red hose here. On this channel, we need to know what the flue is, or inside of the flue, with reference to the CAZ. So we leave this one open because it's in the CAZ, or the combustion appliance zone. We put our red hose on here, and we stick the metal probe right inside of this hole in the venting system or the flue. Now our manometer will be able to sense a couple of different pressures. The pressure of the CAZ with reference to the outdoors, and the pressure of the flue with reference to the CAZ. I'm going to go ahead and turn my manometer on, so I hit the on button. Give everything just a second to get dialed in there. It's also important to make sure you're not standing on your hoses as you're doing this. Once we turn that manometer on, we want to establish a baseline, okay? Or basically zero the manometer. So I push baseline, start. And it's going to start counting down over here on this side. You can see it counting down in seconds. Give it roughly 10 seconds. And then hit enter. Okay, we've now established our baseline. What this is showing us is on channel A that our CAZ, in reference to the outdoors, is at zero pressure. There's no difference between the pressure in here and the pressure outside. This is showing right now that the difference of pressure between our flue and the CAS is negative 0.2. So there's very minimal pressure difference in here. It's critical to know the pressure difference because we need to understand how this affects everything. And the laws of physics tell us that air will always move from a higher pressure to a lower pressure, okay? We'll talk more about that a little bit later when we start the CAS testing. Once we've established our baseline, we want to walk through the house and turn on the various appliances that may have a negative impact on this CAS. If we make this CAS, or combustion appliance zone, more negative or less pressure than the outdoors, the laws of physics tell us air will move from the higher pressure to the lower pressure, and one of the ways that the air will move is through this venting system, because it goes from the top of the water heater directly to the outdoors at the roof. And if there's less pressure in this room than there is outside, air is going to want to move from the outside through this vent, or in the reverse direction. Remember, when this is running, we want all those flue gases to go out. And if there's a big enough pressure difference, those flue gases will come back into the house, and we don't want that. So the next thing we're going to do is we're going to walk through the house and we're going to turn on all the appliances that may have a negative effect on this, or things that may make this CAS go negative. Okay, so we've set our manometer up. We're ready to go through the house and start turning on the appliances that may adversely affect our CAS, or our combustion appliance zone. So follow me through the house and we're going to flip some fans on. Okay, in this bathroom we have two exhaust fans. Exhaust fans suck air out of the house, so there's a potential for them to cause that CAS zone to go negative by sucking air out of the house. So we want to make sure we turn both of those exhaust fans on. They're running. We have a few more exhaust fans in the house, so let's go find those and turn them on. Okay, in the kitchen we have a over-the-range vented range hood. It has two choices, high or low. We want to create worst case conditions, so we're going to go ahead and turn that on high. In the kitchen we also have one more fan up here. It's operated by a wall switch over here. We just go ahead and tap that and turn that fan on also. Now let's go back into our CAS and see if that's had any effect on our pressure in the CAS. Okay, remember when we hooked our manometer up and started, our CAS pressure with reference to the outdoors was 0, or basically no pressure difference. Now with those exhaust fans running, our CAS pressure has changed to -1 Pascal. That means that this CAS, or combustion appliance zone, is more negative than the outdoors, or the outdoors has more pressure than the CAS. The laws of physics tell us that air will move now from the outside of the house to the inside of the house through holes in the house like this flue. And we can actually watch that happen by using a smoke stick. And if I apply smoke here, you can see which way the air is moving the smoke. Air is moving back down that flue and pushing into the house. Well, the water heater's not running yet, so that's not necessarily a bad thing. But if this water heater was running and that pressure difference was causing the products of combustion to roll back into this house, that's going to create problems in the house. We're going to have moisture and carbon monoxide building up in the house. That's the purpose of this testing. So let's continue. There are a couple more appliances in this home that may adversely affect this CAS. One of them is right here in the mechanical room with us. It's a dryer. Dryers have exhaust vents and they exhaust air to the outside. In order to do that, they have to pull air out of the house. So we're going to go ahead and turn the dryer on. Let's see if the dryer affected our CAS. Okay, turning on the dryer made our CAS go slightly more negative. We're now to -1.5, 1.6 Pascals. So again, air is going to be moving down this flue into the CAS. Okay, we also have an air handler that may adversely affect the CAS because it has a fan inside of it. And that fan will move air. So we're going to go ahead and turn this air handler on as part of this test. Takes just a minute for our fan to get up to speed, so we're going to give it roughly 30 seconds, 45 seconds to let that fan get up to speed. Okay, now our fan in our air handler or furnace is up to speed, and we can again see by turning on that air handler, we have made our CAS go even more negative. We're up to now negative 1.9 or 2 pascals. So remember the laws of physics, our CAS is more negative or less pressure than the outdoors. The laws of physics tell us that the air is going to move from the outdoors into our CAS through any opening it can find, including the venting system for our orphaned water heater. There's one more thing we need to do for this worst case draft test. We have various doors in here. We need to see if our worst case condition is with the doors open or closed. Right now the doors are open and our CAS is negative 2 pascals. Let's go ahead and close these doors and see if that creates any sort of difference. Okay, we can see with the doors closed that our CAS, or combustion appliance zone, has gone even more negative. We're now down to negative 3.2 pascals. You can also see that our flue up here is positive 1.4 with reference to the CAS. Remember the laws of physics, air will always move from positive to negative or from high to low. So again, we're going to show you that. You can see how rapidly that air is being pulled back down through the flue. Now our hope or our goal is that when we fire up this water heater, the heat of the combustion byproducts or the flue gases will heat this up and cause that to start to vent properly. Natural draft appliances depend on the fact that hot gases are buoyant and they will want to float up. The other thing you need to be aware of is for a natural draft appliance to vent properly, this relationship to the CAS, this flue has to be a negative number. Okay? The CAS has to be more positive than the venting system because remember the laws of physics, air is going to want to go from the more positive CAS up the vent. Right now our vent is more positive than the CAS and the laws of physics tell us only one thing is going to happen. Air is going to move down this, and we saw it using the smoke stick. So BPI has some standards regarding CAS depressurization. Well, I can't remember all the standards, so I'm going to refer to my quick reference card. The BPI tells me that if I have an orphaned natural draft water heater, my CAS depressurization limits are negative 2 pascals. That means if my CAS, or combustion appliance zone, is any more negative than negative 2, I fail. Well, my CAS right now is negative 3.3. So that means that this CAS fails this test. So you would note to the proctor that the CAS, worst case depressurization test in the CAS, this CAS fails. If this number was anything above negative 2, it would pass. Okay? The next step we need to do is we need to actually fire this water heater and see if it will develop enough heat and enough buoyancy in this flue to overcome this negative pressure and vent properly. Now BPI also gives us some guidance on what they call spillage. Spillage means that if this is running and the flue gases are spilling out of this opening, the draft diverter, instead of going up the vent where they should be, then it's spilling out into the room. So again, because I can't remember all the standards, I turn to my quick reference guide, and BPI tells me acceptable appliance spillage periods. For a water heater, I have 1 minute. That means that when I turn this water heater on, I have 1 minute or 60 seconds for it to develop a good draft. Now, one thing you guys need to understand is that almost every natural draft appliance will spill a little bit on startup because you usually have a cold flue and it takes a little bit of time for the hot gases to heat that up and allow that hot buoyant air to rise up out of the flue. So a little spillage on startup for any natural draft appliance is pretty common and normal. The key is, will it develop a good vent within a certain amount of time? The BPI standards are 1 minute. If it's still spilling after 1 minute of time, then it fails the worst case spillage test. So a few ways we can check spillage. I have a piece of glass here, a mirror works, okay? I'm gonna set this right here. We're also going to watch our gauge. We know from the laws of physics that if this number, the flue with reference to the CAS, is positive, that thing will not vent. This number has to be negative. If flue gases are spilling out of here when I start this, you're going to see them condense on this glass. The flue gases are hot and moist. They hit this glass, which is colder. They're going to condense on there, and you'll be able to physically see that. And then we can also use smoke to physically see that happen. Now, BPI says you have to do this for 60 seconds, so I'm going to go ahead. I'm going to get my stopwatch out or my smartphone with a timer in it, whatever works for you. And you need to go ahead and set a timer. Okay, I've set my timer for 1 minute. I go ahead and I turn the water heater on. Make sure it does fire, either by hearing the burners fire or I can visually see them fire. I start my timer. Okay, now we can see the condensation on this glass. You can see the hot flue gases are spilling out, and you can see it build up on the glass. We're going to use a little smoke. If this is venting properly, that smoke should be going up the flue. It's not. The flue gases are spilling out and pushing that smoke back into this room. That means that this water heater is spilling moisture and carbon monoxide into this room. That's why we wear a personal CO detector while we're doing these tests. We can also see that our vent pressure with reference to the CAS is still positive. As long as this is a positive number, this vent will not work properly. Again, we can see the condensation. If you hold your hand here, you can feel the heat on your hand, you can feel the moisture, and you saw the smoke. We have to time it for 1 minute. Our timer is almost up. Okay, 60 seconds has elapsed, and this appliance is still not venting properly. So it fails the BPI worst case draft test. At this point, go ahead and shut the gas off. So simply turn this knob back to the pilot lighting position. Okay, BPI has some guidance on this. They tell us if you fail the worst case draft test, go ahead and return the house to natural conditions and test again. See if it will pass under natural conditions. That's what we're going to do next. So we're going to go ahead and walk through the house and turn off all these appliances and open the doors. Okay, both those bath fans off. Range hood off. Kitchen exhaust off. And of course the last thing we have running is our fan or air handler or furnace. We're going to go ahead and shut that off. Okay. We've returned our CAS to natural conditions. Now BPI wants us to go ahead and test again in natural conditions, and you can see with all the fans turned off that our CAS, with reference to the outdoors, we were up to -3 pascals. We're back down to -0.1. And notice our flue. Our flue with reference to the CAS, because now that flue is hot, is negative 0.9 or almost 1 Pascal. Now remember what I said earlier about that flue. As long as this number is negative with reference to the CAS, air will always move up. You can see now that we have a pressure difference here where the flue is less pressure or more negative than the CAS, our smoke is being sucked right up the flue. And the water heater's not even running right now. It's just the residual heat in here that's allowing that to happen. Okay? So now BPI wants us to test again under natural conditions. Okay, so I'm going to go ahead, we're going to put our glass back in place, and we're going to see with the glass, the smoke, and the pressure, will our water heater vent under natural conditions? Now if you ran this water heater and got this flue really, really hot, BPI says that you need to let the flue cool down before you do this test again. Okay, we didn't run ours very long, it shouldn't be too hot, so we're going to go ahead and fire the water heater up again. Again, I'm listening for the burners to fire, and I can visually look through the viewport and see that the burners are on. Now you'll notice I'm not seeing any condensation on that glass. Notice what's happening to our flue pressure in reference to the CAS. The hotter that gets, the more negative that goes. And the more negative that number is, the stronger that draft is going to be. Natural draft appliances operate under a negative or non-positive pressure in the flue. Okay, remember the laws of physics. Now our flue is more negative or less pressure than the CAS, so the air will move out of the flue. We can see we're not spilling. We can see that we got a good strong negative draft, and I can watch the smoke. You can see we have a good strong draft sucking the smoke right up the flue, and the products of combustion are going where they need to be, out of the house. Okay, so under natural conditions, we're venting just fine. Now BPI gives us some guidance on how strong our draft should be. BPI gives us a formula, and the formula is right here. Acceptable draft test ranges, and it's based on the outside temperature. If the outside temperature is less than 10 degrees, our draft pressure needs to be at least negative 2.5 or something stronger. So negative 3 would be good, negative 3.5. Anything less than negative 2.5, for example, negative 1 or negative 2, would not be a good draft if the outdoor temperature is less than 10 degrees. Well, our outdoor temperature falls somewhere in here, between 10 and 90. So we have a formula. Okay, we can check the outdoor temperature over on our thermostat. So you can simply walk over here and look, and it will say outside. So we know our outdoor temperature right now is 73 degrees. That's the first piece of information we need for our formula. Okay. I'm not good at math in my head, so I'm going to use my calculator. You're welcome to have a calculator when you take the exam. So the formula tells me I take the outdoor temperature of 73 degrees, divide by 40, minus 2.75. Leaves me with 0.925. That means that my draft has to be negative 0.9 pascals or better. Okay? I'm way better than that. I'm negative 4 pascals. Okay? So I pass my draft test according to BPI standards under natural conditions. Okay? At this point, you're going to go ahead and shut the water heater off. Stop. Okay, so we've passed our draft test under natural conditions. There's one more thing we need to check. We need to check the CO levels, because BPI gives us guidance on what we should do based on what has just happened. We failed under worst case, we failed our CAS, but we did pass under natural. So we need to check CO or carbon monoxide levels. So we're going to take our carbon monoxide analyzer, and we always turn this on outside. Okay, we zero it outside so we know we're in a clean, carbon monoxide free environment. BPI standard says that's how you do it. So I'll simply step outside, turn this on by hitting the power button. This takes 1 minute to warm up. That has a timer on it. It'll count down 60 seconds. So we're going to go ahead and let it warm up for 60 seconds. Okay, so our combustion analyzer has warmed up. It's ready to go. Once it gets warmed up, you'll see on the screen, and you can see it says hold up here. It's important that you remember to push the run hold button, and this needs to say run when you start your testing. Okay, critical that you remember that. That needs to say run. Okay, we're ready to start the CO testing. And by the way, you just left your water heater running. Okay. Probe placement is critical when you do this. On a water heater or any natural draft appliance, you don't want to take this reading up here, because you'll get a skewed reading because we're going to have dilution air entering the draft hood. So this reading needs to be taken underneath the draft hood with the probe down in the top of that flue right there. Okay, you don't want the probe up here, you want it down inside. Now sometimes you may even have to drill a hole in this draft diverter here to get that probe down in there. In this case, we can just stick it in there. And it takes just a little bit of time for this to start doing its sampling, but we're just watching this screen here. And the number we're concerned with for this test is the third one down that says CO, carbon monoxide. We can see that it's coming up a little bit. We're getting a couple of parts per million. So we want to just leave this here and take this reading until it kind of steadies out. You'll see all those other numbers are jumping around. As soon as the numbers stop jumping around and become steady, then you can call that a good reading. And it may take up to a minute and a half for those numbers to stabilize. Okay, they're kind of slowing down a little bit. We're probably going to start to stabilize out here pretty quick. So you can see our third number down, carbon monoxide, 26 parts per million. Okay, that's the critical piece of information we need from this. We're going to go ahead and take our probe out. We're going to set our combustion analyzer aside. Now BPI gives us some guidance based on all the testing we've just performed. I'm going to turn to my BPI standards. The proctor may ask you, what recommendations are you going to make to the client based on the testing you just did? So BPI tells us our CO test result, we were 26 parts per million, so we come down to this box here, and our spillage and draft test results fails at worst case only. So this is the line we're at for this test. Okay, we did not pass up here, we did not pass up here, we fell at worst case only. Okay, and so we come across here, and our recommendations should be recommend a service call for the appliance and or repairs to the home to correct the problem. Maybe they need to add more combustion air in this room to offset that negative pressure. Maybe there's something wrong with the venting system. Okay, but that is the recommendation that you would make based on the testing you just did in this combustion appliance zone, or CAS. Okay, that's the end of the combustion safety module. Okay, the next module we're going to cover is the health and safety module. This module only applies to the envelope professional. So if you're taking the building analyst field test, you don't need to worry about this module. For the envelope professional, you will. So part of the health and safety is to check for moisture related issues. So on this house, we would just kind of make a note. We're looking at the house. We see we have no rain gutters up here. So when it rains, water could come off of this roof and get back into the house through here. So we have an area where we could have potential, for moisture issues with water seeping back into the house through the doors or maybe through the foundations. So that's one thing we know here. Let's walk around the house and through the house and see if there are any other health and safety issues we need to be concerned with. So over here we have a crawl space. I'm going to go ahead and open the crawl space up. For your BPI field exam, the assumption of this crawl space is it is a dirt floor. In real life it's concrete, but for your exam you're going to assume this is a dirt floor. Well, this is a moisture issue here, okay? Again, water can get in through here. We have a dirt floor. Moisture can seep up through that dirt and it could affect the house. So that's something you're going to want to point out and make recommendations about how we can control that moisture. Perhaps a vapor barrier of some sort would be recommended here, okay? So this is another area of moisture or health and safety that you need to be concerned with. Let's go ahead and go into the house and look in there and see if there's any issues in the house. Okay, in the house, obviously, we have a bathroom with a shower. Okay, a shower is a potential source of moisture contamination, along with the tub. People shower in here, they bathe in here, you're gonna have a lot of moisture in this bathroom. So you would wanna make a recommendation to somehow help control this moisture. Exhaust fans, okay? So if you had a home with a bathroom with a shower and a tub and there was no local exhaust, that's a recommendation you'd want to make to the homeowner because of the moisture issues associated with a shower and a tub. Let's see if we can find any more health and safety issues. Okay, another one is this fireplace. We have a wood-burning fireplace here. So we want to make some recommendations about this. First of all, it could be a potential fire hazard if we get sparks out on the floor. Definitely a source of contamination if it's backdrafting or something like that. So we want to make a note of that and discuss that with the client. This is a potential health and safety issue and make some recommendations as to what steps they might take to help prevent that. Maybe some screen or glass on the front to prevent sparks, maybe replace it with a gas insert or something, but we need to be aware of that health and safety issue. Another health and safety issue and source of contaminants in this house, of course, is our gas oven and cooktop. Again, we're giving off products of combustion, which contain carbon monoxide and other poisonous things, and a lot of moisture. There's tons of moisture in this exhaust and stuff that comes off of here. So we want to make recommendations to deal with that. Again, localized spot ventilation is a good way or a good recommendation to take care of that particular health and safety issue. Let's go through the house and see if there's any other health and safety issues. We're going to go ahead and go upstairs. Okay, the other thing we want to look at here is we have this knee wall and with an attic behind it. And inside this attic, you can see we have some knob and tube wiring, very old wiring. Definitely a fire hazard, and especially if we were to insulate over the top of that knob and tube wiring. So you're going to want to make a recommendation to the client, and the proctor may ask you during your testing, what recommendation would you make? You would need to do something to address that knob and tube wiring. Perhaps the recommendation is to get a licensed electrician to come out and replace all the knob and tube wiring with updated wiring. Or at the very least, develop an insulation and air sealing plan for this attic where you will not cover that knob and tube wiring. That may be very difficult. Probably the best option would be to have an electrician come and upgrade that wiring. Okay, the next module we're going to go through is the carbon monoxide or CO testing. This module is required for both the building analyst and the envelope professional. So whichever two of those designations you're taking, you'll have to be proficient at this module. Again, we have our carbon monoxide detector or combustion analyzer. The key to this is remember to always turn this on outside. Now we turned it on outside before we did our water heater, so I have it running here. We have some other gas appliances in this house that we're going to go ahead and check. The next one is the furnace. Now remember, you've already tested your water heater when you were doing your combustion test, your CAS test, so you don't need to go back and do the water heater again. The proctor will note that you've already covered the water heater in the CO testing portion. But we do need to check the furnace, and we have a gas range, so we need to check that also. So I'm going to go ahead and I'm going to turn this furnace on. Okay, the furnace is going to start up. Now before you start taking your readings, you need to allow the furnace to fire, and it needs to run for a couple of minutes so that everything can get stabilized in here. So we're going to go ahead and let it fire and run for a couple of minutes. Okay, so we've gone ahead and fired up our furnace. It's running. We've let it run for a couple of minutes so that the combustion process can stabilize. Now we're going to go ahead and do our carbon monoxide or CO test. We have a hole conveniently drilled in the exhaust pipe for you. We're just going to go ahead and stick the probe in there. And again, it takes just a little bit of time for this to start sampling, but we're going to be watching the screen, and we're concerned with the third number down, CO or carbon monoxide. So we're just going to let that run, get it sample, and start giving us a reading here shortly. Okay, so our numbers have finally stabilized. It takes a couple of minutes to do this. You can see again the number that we're concerned with for this test is CO or carbon monoxide, and we're at 19 parts per million. Okay, BPI gives us some guidance on this, so let's go ahead and take a look at our BPI standards. And in our BPI standards, we're basically 0 to 25 parts per million, so we're just fine. We can proceed with work. If at any time you get a reading over 100 parts per million, you're going to want to make a recommendation to the client that they have service performed on that piece of equipment. Okay, for a furnace or a water heater, over 100 parts per million is an action level. Make a recommendation for service. Our level is very low, we're perfectly good there. So let's go ahead, we're going to do a CO test on the gas range next. Okay, the next appliance in our house that we need to do a carbon monoxide test on is our gas range. Okay, we're going to go ahead and do that test. Very, very important. Before you do the test on the gas range, check inside to make sure that there's no leftover debris that may catch on fire, or food or anything like that in there before you do this test. Very important. So we check there. And also check underneath. You don't want anything inside that range when you fire it up. Okay, we're going to go ahead and we're going to turn the oven on. We're going to turn it up to its highest setting. Give that a minute to fire up. We're going to take our combustion analyzer, and remember, we've already started this outside. We started outside where there's no CO, so we know that we've started in a clean environment. Also remember your personal CO detectors. Okay, always monitor the area when you're testing. And in order to get a sample, we're going to stick the probe down inside of the flue. We got to make sure we're down in the right place. We want to get a sampling of where the flue gases come out. Okay, some ovens may have the flue on one side or the other. This one is in the very back, and we want to get the probe right down into that flue. Again, it's going to take a minute for this to fire up and start sampling. Okay, so we have the oven on, we have our probe in the proper location, and we can see something here. We have carbon monoxide, CO, at a level right now of 700 parts per million and climbing. That's why when you're doing this testing, it's critical to have your personal CO detector on. Levels of carbon monoxide like this can cause very serious problems and even death So you need to be aware of what's going on. These are very high carbon monoxide levels. So we want to make sure we're wearing a personal CO detector while we're doing this, because if we get exposed to high levels, we need to end the testing. Okay? BPI gives us some standards. I'm going to go ahead and turn to the BPI standards for ranges and ovens. BPI says if we're greater than 300 parts per million as measured, the unit must be serviced prior to work. Okay? So the recommendation that we're going to make to the client is that this unit needs to be serviced, and if the CO production still maintains a higher than 300 parts per million after service, exhaust must be installed, and we do have exhaust installed on this one. Okay, you can see why exhaust is important, because we have a lot of carbon monoxide being produced and dumped into the living space. Also moisture. Okay, so make sure that when you do your CO testing on this range, you know the BPI standards and you let the proctor know. And the proctor may ask you the question, what recommendations would you make to the client based on your testing? Let's go ahead and shut this off. And I'm going to ventilate because we just dumped a lot of carbon monoxide into the kitchen. Okay, that concludes the carbon monoxide or CO testing module. Okay, the next module we're going to go through is the duct system inspection. This particular module only applies if you're doing the building analyst exam. You don't need to worry about this if you're doing the envelope professional exam. So a few things you need to be proficient at this is recognizing what the ductwork system is. So you'll need to be able to point out to the proctor that we have supply ductwork here. This is the ductwork that delivers the conditioned air to the house. So you'll need to be able to note the difference between supply ductwork, which delivers the conditioned air to the house, and the return ductwork, which allows the heating and cooling system to pull air from the house back into the system. So air is pulled into the furnace and it's either heated or cooled depending on what's running, and then it's delivered through the supply ductwork to the rest of the house. So you need to know the difference between return and supply. Another thing you're going to need to be able to do is point out where the filter is and mention to the client the importance of changing this filter. Now you'll notice I flipped the furnace off. It was running. I turned it off before I get in here. We find the filter. We want to inspect it. Okay, it's not horribly dirty, but the recommendation you're going to make to the client is change your filters, keep clean filters in all the time. Okay, we're going to go ahead. The ductwork in here is sealed up very good. You can see all the joints are sealed. We don't see a lot of areas where there's leakage. One area where there would be some leakage, we can see on this pan return here where the pipes pass through the floor joists. Those are areas where you're going to want to make recommendations for air sealing. You can see on the copper plumbing lines, we have air sealed those ones, just a little bit of foam. And again, back over here, the ones that are not sealed. That's an area of ductwork leakage, and your recommendation should be to seal those areas up. The rest of the ductwork in the mechanical room that we can see looks really good. There's one other area that we want to go look at, and that's in the crawl space, because we have ductwork that goes into the crawl space. And the crawl space is outside of our thermal envelope, or it's in an unconditioned area. And it's very, very critical that that ductwork is properly sealed and insulated. So let's go into the crawl space and evaluate that ductwork. Okay, we've moved into our crawl space and we're going to evaluate the ductwork that's in this crawl space. This is especially critical because this ductwork is outside of our thermal envelope, or it's out of the conditioned area. So any duct leakage out here can create big problems within the thermal envelope. So we're going to go ahead and evaluate this ductwork. Okay, so in evaluating or looking at this ductwork, we can see we have an area of major issue here. We have a big tear in the metal. We have an end cap that's coming off. There's a big leak here. This happens to be on the return air side of the duct. So whenever the fan inside is running, it's sucking air from this crawl space into the house. Now this crawl space could be full of contaminants. You know, we have a dirt floor, we have rodents that live in here, bugs that live in here, whatever. You know, you throw a bug bomb down here to kill the spiders and your furnace is running, you're pulling all that stuff into your house. You can see some areas of concern here, okay? Holes in these floor joists. These are all areas that we're gonna highly recommend duct sealing. This all needs to be sealed up nice and tight. The other thing you'll notice is our ductwork is lacking insulation in various spots. BPI standards say that any ductwork outside of the thermal envelope or the conditioned area need to be insulated to a minimum of R5. Okay, you'll need to be familiar with that standard. The proctor may ask you that question. So your recommendation to the client on this ductwork is going to be duct sealing and proper insulation to bring it up to the BPI standards of a minimum of R5 on the ductwork. Okay, that concludes the duct inspection module. Okay, the next module is the hydronic steam distribution inspection module. You don't even have to worry about that module. Since we don't have hydronic heat or steam in this house, that one's not applicable. So don't worry about it, just skip right over it. You're not gonna be graded on it. Okay, the next module we're going to be going over is the Infiltration Evaluation. This module needs to be covered and you need to show proficiency at it in both the building analyst and the envelope professional. So this is where we're going to run a blower door and we're going to do some zonal diagnostics and we're going to evaluate how leaky the house is. Now of course the first thing that you're going to need to do is you're going to need to set your blower door up. Part of the field test is you're going to have to show proficiency in assembling and installing this blower door into the door. I've already done it for you, but you need to make sure when you come here on the field test that you know how to set this blower door up, okay? Once you physically set the blower door up and got the blower in, then you want to go ahead and hook your hoses up, okay? The red hose goes to the input on channel B. The green hose, which is run through a hole in the blower door and stuck outside, and it's important to make sure that the other end of this hose is about 5 feet away from the fan, so I just run it down the side of the house. The green hose goes to the reference port on channel A. So we're going to get a blower door reading with reference to the outside. Okay. We get this all set up. Now the next important step is to make sure that the house is set up in wintertime conditions. So you need to walk through the house and you need to make sure that all the windows and exterior doors are closed, just like the house would be in wintertime. You also need to make sure that the water heater is turned off. Okay, so you're going to go in and actually turn the water heater to off or turn it to the pilot setting. The air handler or furnace must also be turned off, so you're going to want to make sure it's turned off. And you want to make sure that there's no fire in the fireplace. Okay, if the fireplace is on, make sure you turn it off before you do your blower door. These are all important safety things. If that fireplace was running or a fire was in a fireplace and you turn this blower door on, because we're going to be sucking air out of the house, you'll suck the fire right into the living room. Same with gas appliances. If they're running a natural draft appliance, you'll pull all the products of combustion or flue gases right back into the house. Okay, so we've set our house in wintertime conditions. Our blower door's set up, we've got our gauge set up properly. Now we're going to go ahead and turn our gauge on and run a baseline. So the first thing I'm going to do is turn the gauge on. Let that get started up. Now I'm going to hit the mode button. I'm going to hit it 1, 2 times. I'm going to go ahead and turn the back light on. Maybe you can see that a little better. You want your gauge to say BD3 open, and we're looking for pressure flow at 50. Pressure flow 50. So again, on, hit the mode button twice. Once you see that you're on blower door 3, open ring, pressure flow 50, then you're going to hit baseline, start. Again, this is going to count down for about 10 seconds. You can see it counting down on this side over here. Once that gets down to 10, we're going to go ahead and hit enter. Okay, so we've got our manometer, our DG700, properly set up to run a blower door depressurization test on this house. I'm going to go ahead and remove the ring. We've set our manometer to run an open ring, so we're going to remove the whole ring segment and run this with an open ring. I'm going to go ahead and start the fan now for depressurization. Now, some of you may be familiar with the cruise control feature of the DG700. If you are and you want to use the cruise control, that's fine. I'm not going to use cruise control for this example. I'm just going to go ahead and start the fan. Now, what I'm looking for here is negative 50 pascals. And you can see we have a problem going on here. I've got this fan turned all the way up, and we didn't get above 5 pascals. We're just barely above it. That immediately to me is an indication that something has happened. I've missed a door or I've missed a window when I did my walk around to set it for wintertime conditions. Let's go ahead and take a look and see what happened. Once I depressurized the house, air started to want to move into the house, and apparently I did not check this door to make sure it was shut tight. Okay, and that door popped open, so it didn't allow my blower door to operate properly. Now that I've ensured that it's shut tight and we've made sure that all the exterior doors and windows are shut, let's try that again. Okay, again, I'm going to start the fan, and I'm looking for a number over here of negative 50 pascals. And just gradually turn that up. Now you can see we're going to start getting a CFM reading over here. It's telling us how much air is leaking into this house when we use the blower door. Now you don't have to get this to exactly 50. As long as you get it above 45, the little computer inside the manometer can do the math, and the numbers you get will be accurate enough. Okay? We're going to get it up there close to 50, or at least above 45. It's up to you if you want to play with it a little bit and fine tune it and get it right up to 50. Okay, now that we've got that established, we can see that this house is currently leaking 3,500 CFM roughly. You'll see these numbers jump around, okay? You can actually eliminate the jump if you change your time average to long. So if you don't like the jumping around, I've changed it to long. I'll slow that jumping a little bit, give you a more steady number. Again, our average, or the number it seems to like to be at, is around 3,500. So that tells me that this house, when it's under negative 50 pascals or depressurized, is leaking 3,500 CFM of air into the house. Think of 1 CFM as a basketball, okay? Under negative 50 pascals, this house is leaking 3,500 basketballs per minute from the outside to the inside of the house. Now at this point, the proctor may ask you a question. The question is going to be about the building tightness limit, and how tight can we make this building? How much can we change this number before we're going to run into problems? There's a formula to determine that in the BPI standards. And it's a little bit confusing, so we're going to take a little bit of time to go over that formula and make sure you understand it. Okay, so the proctor may ask you a question about the minimum building airflow standard or the building tightness limit. It's basically, how tight can you make this building? Remember our blower door number, we were leaking 3,500 CFM. So how tight do we want to make it? What do we want to get that number down to? And there is a point where you can get it too tight. And if you make a house too tight, you need to prescribe ventilation for that house. The analogy I use for making a house too tight is, imagine I put a plastic bag over your head and seal it off. Eventually you're going to have serious problems. The same thing applies to a house. If you make it too tight and don't provide ventilation, you're going to have indoor air quality problems. Contaminants are going to build up in that house, moisture is going to build up, and it's going to cause a lot of issues. So you need to be able to understand this formula, and you need to be proficient at it. You're going to have to demonstrate it for your proctor. The BPI standards give you the formula, and you can follow right along. I'm going to do it on the whiteboard for you so you can see it. In the field test, if you forget or get confused, just refer to your BPI standards and go right through the formula. So the way the formula works is it says take the number 0.35 times the volume of the house. The volume of our house is 12,500 cubic feet. So 0.35 times 12,500 equals 4,375. The next step is to take 4,375 and divide that by 60. Okay? That equals 73 CFM. What that is telling us is based on the volume of this house, it requires a ventilation rate of 73 CFM. Okay? And I just followed that right from the BPI standards. Now the next thing they want to know is what is the ventilation rate based on the occupants? Well, our house has 4 people in it. The formula for that is 15 CFM per person. 15 times 4 equals 60 CFM. You need to know both of those numbers because the next formula that we're going to do requires you to pick the largest of those two numbers. So obviously the largest of these two numbers is this one, 73 CFM. So for the next part of the formula, we need to know a few things. We need to know our N factor and what zone we're located in. And again, that's right in the standards for you. So Utah is located, or where we're at in Utah, is located in Zone 2. So we're going to use the Zone 2, and it gives us an N factor that ranges anywhere from 17 to 20. So the question is, which number do I use? 17, 18, 19, or 20? Use whatever number you want, but I always err on the side of caution and use the largest number. So I'm going to use 20. The other thing we need to know is our height correction factor, and it gives us numbers of stories for the dwelling. Our house happens to be 2 stories, so our height correction factor is 0.81. So now that I know those two numbers, I can finish off the formula. I'm going to take 20, which is my N factor, times 0.81, my height correction factor, and that equals 16.2. Now I can finish the formula. Again, I can go back to my BPI standards, and it tells me my minimum CFM, or the tightest I can make my house, would be my highest CFM calculation times my corrected N factor. So let's put the math to that and see what we come up with. So I'm going to take 73 CFM times my corrected N factor of 16.2 equals 1,183 CFM. That simply means, remember the number on our blower door. Our blower door said our house was leaking 3,500 CFM. If I make the house any tighter than this, if I get that number to reduce down to this, I need to prescribe additional ventilation for that house. BPI has the standards for that in the standards guide. You need to be aware of this formula. You'll need to be able to demonstrate this formula during your BPI field test. So it's important that you practice and familiarize yourself with this formula. The volume of our house is 12,500 cubic feet. Okay, so we determined our building tightness limit with the formula. The way you use that formula is remember the number we achieved inside of the whiteboard. It was 1,182 CFM roughly. That tells us that when we start to air seal and tighten this house, when we run our blower door when we're all done, this number had better not go below that number we determined using the formula. If it does, we're going to need to prescribe additional ventilation for this house. Okay? We can't get the house too tight. If you get a house too tight, you're going to run into issues. So that's what that formula is determining for us. How tight can we safely make this house before we need to add ventilation? Now we've got our blower door running again. We're back up to negative 50 pascals. We're going to take a smoke stick and our hand, and we're going to walk through the house and just kind of find air leakages, determine where air is leaking in this house, and talk about some of those air leakage areas. We're going to go ahead and start up here in the addition of the house. Now what we have here, and we've made this very easy for you guys, you can see we have a penetration through the top plate of the framing into the attic above us. Air will move through that penetration. You can also see we have a crawl space underneath us. And we have some very large penetrations from the plumbers installing the tub into that crawl space. Those are two areas where air can move from outside of the envelope to inside, or vice versa, depending on the conditions. Because our house is under negative pressure right now, our house is more negative than the outside. So remember the laws of physics. Air will always move from high pressure to low pressure. So right now the house is a lower pressure than the outside. And we can visually see through the pocket door. If the camera can zoom in on that, you can see which way the air is moving. It's moving through those penetrations, through this pocket door, into the house. Not only can you visually see it using the smoke, you can stand here and feel it with the back of your hand or your face. The back of your hand and your face are great tools to feel airflow. You can feel tremendous amounts of air leaking through this pocket door because of those penetrations. These are items that you'll need to be able to point out and explain to the proctor as you're doing the BPI testing. Let's take a look at a few more examples. Here's another one that you may want to point out to the proctor. We have a striker plate for this door. This wall that the striker plate is in connects to the attic above us, and there's wires and plumbing in here, and that attic communicates with this striker plate. And that hole in there allows air. Again, if the camera can zoom in on that, you can see the direction of the airflow. Okay, that's another air leakage spot. Air can move in and out of the house through spots like this. Let's take a look at a few more. So again, as I walked in here, I could feel some air movement up here. So I'm going to put some smoke to it. And you can see air is blowing out of the cabinet. Well, let's take and open that cabinet and see what's going on. My range hood is vented. That vent runs up through the attic to the outside. And so I've got some areas here where I have leakage. Now you're going to want to recommend to the client, or the proctor may ask you, what would you do to fix this? A very simple solution would be a can of spray foam. Spray foam around that penetration. Or get in the attic and spray foam it from the top. Okay? So it's important to know what kind of recommendations you're going to make. Some other issues that you'll notice, we have some can lights. Can lights are areas of large leakage. We'll be able to see those better from up top. Again, we have an attic above us. That attic has floor joists. And I'm going to go ahead and add some smoke to those floor joists, and you'll just watch that area up there. We're going to watch how the air moves. see the air movement is from the attic through those floor joist spaces, and smoke is actually coming out of the light fixtures. You can see a little bit out of the can lights. Now the easy fix for this is some rigid foam board, and again some spray-on foam. Where we've blocked that floor joist, we've eliminated that air movement. Again, these are areas of concern that you need to be able to pick out and show proficiency at understanding how air moves and how you might correct those. Another item we're going to look at, outlets on exterior walls. Once we put some smoke to that, very good visual on which way the air is moving. You can see the air is blowing the smoke into the house. Again, because the house is less positive than the outside, air is going to move from the high pressure to the low pressure. Okay, it's laws of physics. Let's go ahead and take a quick look upstairs. Okay, now we're upstairs. Here we have an old window, old leaky metal frame single pane window. So let's use our smoke stick to take a look at this. Again, a very good visual. You can see the air with the smoke being pulled in right through the leaky window, rushing across the window. So another area of concern. At the very least, we need to recommend some sort of gasketing or perhaps new windows altogether. Let's look at another area. We have our knee wall with the attic space behind it. Here we have an unsealed, ungasketed attic hatch on the wall. And you can see which direction the air is being pulled. It's being pulled from the attic or from the outside into the house. Okay, one final one we want to look at. Here you can see on the other side of this wall we have a dropped ceiling. And when they dropped it, we have a connection directly into the attic. This wall communicates with this return air, and the electricians or plumbers have made holes in that. So this is pulling air from the attic right down this wall and into the house through this vent. And again, with the smoke, we can see that. Very good visual. Another thing to note here is anytime the furnace or the air conditioner is running, this return air sucks air in. So it also is sucking air from the attic anytime that fan on the furnace is running, whether it's heating or cooling. So this is an area of big concern. We really need to focus on things like this. We need good air sealing here. So some rigid foam and some spray foam in here would be a great option for air sealing on this. Okay? So we've done a good walkthrough. We've used a smoke stick in the back of our hand to determine the air leakage areas. The next thing we're going to do is some zonal pressure diagnostics. So let's go down and get a diagnostic tool, and we'll start some zonal diagnostics downstairs. Okay, the next thing we're going to do as part of our infiltration evaluation is called zonal diagnostics. Zonal diagnostics can get a little bit confusing, but just pay attention. I think we'll be able to get you through it just fine. We're going to take a second DG700. We're going to put a hose on the input port, and we're going to leave the reference port open. So a hose on the input, reference is open, and it doesn't matter which channel you use. I like to use channel A. Simply turn this on. That's all we're going to do is turn it on. What we're interested in here is in pressure. So we turn it on and it goes straight to pressure. Now remember, this house right now is currently under an influence of roughly negative 50 pascals. Okay? We're negative 46.4. Keep it up a little bit. There we go. Okay? Now we've turned this gauge on inside of that zone, and because both hoses or both ports are in the same zone, our hose and our reference are in the same zone, it has just zeroed itself. It says, okay, I'm at 0. When in reality, the house is at -50, and this is the key to helping you understand zonal diagnostics. We turn this gauge on, both ports are in the zone that's already negative, and so it just sees it as 0. It sees no pressure difference between these two ports because they're in the same zone. So let's go over to the window and show you how we use this to do zonal diagnostics. Okay, I'm going to show you an example here of what we're looking for with zonal diagnostics. Remember, both ports are in the same zone, so they read 0. The machine sees no pressure difference between these two. The house is under -50 pascals. If I stick this hose outside, I'm going to see a pressure difference. If the house is negative, with reference to the outdoors is going to be positive. So let's open the window a little bit. You're going to feel a rush of air come through here. I'm going to stick this hose outside. Close the window down, not so much that I'm pinching the hose. And now you can see I have a positive number on here. And wouldn't you know it, the difference is exactly what our blower door is running. Our house was -50 pascals, so the outside, with reference to the house now, should be positive. Okay, and that's exactly what I'm seeing. I'm seeing a positive number on here, so that tells me that the other end of my hose is connected to the outdoors. And it's obviously connected outdoors. I've stuck it out the window. So we're going to use that information as we go through the house to do zonal diagnostics. But it's key that you understand this relationship. The house is -50 with reference to the outdoors. So when I stick the one end of these ports outside, it tells me, yes, the outside with reference to the house is indeed +50. Okay? Close that window back up. So let's start with some basic zonal diagnostics. What I'm going to do is I'm going to shut the doors in this mechanical room. So let's walk over and shut this door. Now we're going to come over here and shut this door, and we're going to work from the outside here. Now normally what you do is you throw your hose under the door and shut it. But lucky for us, I've already got a hose existing. So I can just simply take this hose, plug it right into the input, and let's see what happens. Now this is telling us that our mechanical room, with reference to the house, is +20 pascals roughly. The closer that number is to 50, the more connected that room is to the outdoors. Remember when I stuck that hose outside, it went to 50 because that hose was right outside, very connected to the outdoors. So this tells me that the mechanical room has a fair amount of leakage to the outdoors. So I want to prescribe or recommend some air sealing on the mechanical room area. And I can use this testing method to narrow down the best places to focus my energy to air seal. So we're not quite to 50, but we're 20. That's almost half of 50, so we've got a fair amount of air leakage in that mechanical room, okay? So let's do a few more zonal diagnostics. Let's go up to the addition and check the bathroom up here. Okay, here we have a bathroom. We have an attic hatch in it. We have some old leaky windows. So there's a potential to have some air leaks into this bathroom. So again, I'm going to take my hose. I'm on the input. I'm going to simply throw my hose into that bathroom. I'm going to shut the door. Once I shut that door, I'm going to see a number over here. Now remember, the closer that number is to positive 50, the more connected this bathroom is to the outdoors. So again, I'm coming in around 18 or 20 pascals with reference to the rest of the house. That tells me that this bathroom has some pretty good air leakage in it. It's pretty well connected to the outdoors. Probably through the leaky attic hatch, probably through the leaky windows. So you're going to want to make recommendations accordingly. This bathroom would be a good area to focus on some air sealing. Maybe by replacing the windows, maybe by putting a gasket on the attic hatch, things of that nature. Let's go upstairs and do a little more zonal diagnostics. Okay, we're back upstairs to do some zonal diagnostics. So I want to know, how connected is this attic to the outdoors? How much time and energy should I spend air sealing this attic? So again, I'm going to take my manometer and my hose. I'm going to open this hatch up a little bit, throw my hose in there, close the hatch, don't pinch your hose off, and evaluate my numbers. Now remember, the last two zones, we had about 20 pascals. This one's pushing 35 pascals. That tells me this attic is really connected to the outdoors. Because remember, the closer that number is to positive 50, the more connected that space is to the outdoors. So there's a lot of leakage into this attic, and of course we have an unsealed attic hatch here. So I would want to really focus my air sealing time and energy on this leaky zone, this attic that is very, very leaky. And we can use this tool to help us determine that. Let's do one more zonal diagnostic before we finish up. I'm going to go ahead, we're going to do a zonal diagnostic of this bedroom. So I'm going to shut this door, and then we're going to work from out in the hallway. So I'm going to isolate this room. I've shut that door. I'm going to take my hose. I'm going to throw the end of my hose into that bedroom, and I'm going to shut this door. And I'm going to see what kind of number I get. Now this time we only get positive 4.5 pascals. Remember, our other numbers were very big. In fact, the attic we were pretty close to 50. The other ones were about half of 50. This one's very small, much closer to 0. That tells me that this bedroom is not very connected to the outdoors. So I'm not going to waste a lot of time or energy prescribing air sealing for this bedroom. I'm going to focus on those areas where I found the biggest air leakage. And this is what zonal diagnostics is going to do for you. You need to be proficient at this on the BPI field test and be able to demonstrate this to the proctor. Okay, the next module we're going to go over is the General Home Inspection module, which is required for the building analyst. You need to show proficiency in this area. And along with that, I'm going to go ahead and kill 2 birds with 1 stone. The other module I'm going to cover while we do the general home inspection is the insulation module, which is only required for the envelope professional. But as you're doing the home inspection, it's very, very easy to just combine those two and get both of them done at the same time. So the general home inspection, we're going to start by doing a walk around the house. We're going to evaluate doors and windows. So we just start, we look at the door, we look at the condition of the door. We know that this door does have weather stripping on it. It's got a gasket, but one issue we note is the door doesn't shut tight. You can see we've got a big gap right here along the top. Okay, so if we pull that, you can see that gap, you can see we're not sealing tight. So a recommendation I would make is adjust the door, perhaps a new door, but we need to make some sort of recommendation or a work order to repair that problem, because that's a nice air leak. So we're just going to continue around the house. We're going to evaluate the windows. Here we have a window that's a nice vinyl frame, double pane. It's probably a relatively tight window, so we won't worry about that. We have another door that closes very tight, seals good and tight. We've got a good gasket on it. Okay, it's a good solid core exterior door. There's probably no recommendations need to be made there. Now we have some windows here. We have some metal pane, single frame windows. Now the proctor may ask you, what is the approximate U value of this window? So we just go to our BPI standards. We can see here that we have a metal frame, single pane. It has a U value of approximately 1.31. That is a very poor U value. Windows like this back here with the vinyl frame, double pane, have a U value of around 0.35. That's much better. The lower that U value, the better. So we would make recommendations about any windows like this, perhaps replacing these windows with something more efficient. We're also just looking again, we've got a dormer up there, we've got another metal frame, single pane. It's a very poor, inefficient window, so we may make some recommendations about replacing that window. Let's go ahead and move on. We have another door we want to check. It's a very old door. It's got a good gasket, but it's got a hard time closing tight. So we would want to make recommendations about how we might fix this door. Perhaps a better choice would be a solid core door, something that's better insulated. So that's a recommendation we'd want to make there. We're going to go ahead and make some recommendations or take a look in this crawl space and see what's going on in there. Now the assumption you're going to make about this crawl space is that it has a dirt floor and it is uninsulated. So you're going to want to recommend a vapor barrier for this dirt floor because we want to keep the moisture from migrating up into the living space above us. I would make a recommendation for air sealing in here. We want to align our thermal boundary and our air barrier. So we want to do that at the floor. So we want to recommend air sealing along the rim joists and along the floor joists, and then recommend insulation. So the proctor might ask you, what insulation would you recommend in here? What would be a good cost-effective choice and what kind of R value? Well, if you do good air sealing, you air seal the rim joists and air seal the rest of the joists, a good cost-effective insulation measure will be fiberglass bats. And again, we can go to our BPI standards and we can find a fiberglass bat. And let's say we can get a fiberglass bat that is 12 inches thick. And if it's installed very good with good air sealing, we can achieve an R30 in here. So again, if the proctor asks you these types of questions, just refer to your standards and you'll be able to find the answer. Okay? The other thing that we'd recommend in this crawl space is we have this big open hole here so the outside air can get in here. So we'd recommend some sort of door on that hole. I'd recommend some sort of insulated and air sealed door, just like what we have here. Okay? Again, we're continuing that thermal boundary and that air barrier, keeping them together. It's important that your thermal boundary and your air barrier are aligned. And we'll see some more examples of that when we get upstairs. So let's continue to walk around the house. Again, you're evaluating windows. What kind of windows do I have? Are they good windows or are they bad windows? Here we have some more metal frame, single pane. So we want to make recommendations about those. We're going to want to check the condition of the sliding glass door. This is good. It's got a gasket. It's a nice vinyl frame, double pane. So it's a reasonably efficient sliding glass door. Let's just go ahead and go inside. We have a couple more windows that we want to evaluate. These are old single pane wood frame windows. So the proctor may ask you, what is the approximate U value of this window? Again, I can just go over here and find I have a wood frame, single pane, has an approximate U value of 0.9. So there are more energy efficient options out there. So we'd make recommendations based on that. Same thing here, we have another wood frame window, single pane. There are much more energy efficient options out there. So those are recommendations we'd make based on our walk around the exterior of the house. So let's go ahead and take a look at some other issues. We have to determine what kind of insulation exists in the walls. There are two different ways to go about doing that. First, we could use a thermal imaging camera. Now, a thermal imaging camera is great if we have areas of the wall that are insulated and others that aren't, because then we can very readily with the thermal camera see the areas that are missing insulation. But if we have an entire wall structure that's completely uninsulated, the thermal imager is not going to tell us that. It will show us one solid color. We have no way to distinguish if it's insulated or not insulated. So the only way, or the best way, is to simply drill a hole in the wall. Drill a hole and get in there and visually inspect. Or sometimes you can remove a outlet cover and get in there and inspect through there, or get a clothes hanger and run it up in there and pull down some insulation and see what exists in the wall. Now be aware, if you use an outlet for an inspection point, there's probably live electrical circuits in there, so be very, very cautious. But usually we'll drill a hole and we'll take a look and see what exists in there. Now in this case, we have a wall stud that's lacking insulation. So the proctor may ask you, what would you recommend here? A good cost-effective solution for this would be dense packed cellulose. Okay, dense packed cellulose, we can drill the wall, we can fill it. It's very cost-effective, it's green, it's made from recycled products. And dense packed cellulose offers us a good air barrier, air sealing, and a good thermal boundary. So our air barrier and our thermal boundary will be aligned. The proctor may ask you what type of R value can you achieve if you dense pack cellulose. So again, we just go to our BPI standards. I have the standards that tell me if I have cellulose at high density, I can achieve an R value of roughly 3.2 Rs per inch. This wall cavity is 3.5 inches thick, so 3.5 times 3.2, I can get an R value of roughly 11 in this wall. So again, you just turn right to your standards to find that. Now also in here we see we have some batt insulation that's poorly installed. It has a big gap. The proctor may ask you a question about this. How does that gap affect that insulation? Well, what happens is air can move through this gap. And if air can move through this fiberglass batt, its R value drops significantly. The proctor may ask you how much it'll affect it. Again, I turn to my BPI standards. I've got a batt that's 3.5 inches thick, so we go down to the 3-4, and I have 3 different levels of installation: good, fair, and poor. Well, it's not good. It doesn't meet the definition of good. Good says no gaps or other imperfections. Fair says gaps over 2.5% of the insulated area. This equals a 3/8 inch square along 14.5 inches of the batt. Well, our gap is a little bigger than 3/8 of an inch, I think. That's more like 3/4 or 1 inch along the whole length of the batt. So that batt would fall into the poor. So we go back down and we look, 3 inches installed poorly. Our R value has gone from 8 to 2. Okay, so again, just use your standards to find the answers to those questions that may be posed to you. Let's go ahead. Oh, one other thing we want to talk about here is these uninsulated walls and the heat loss. Heat will always move from hot to cold. So if we're heating this house in the winter, heat is going to very easily move through this uninsulated wall. We're going to have a lot of heat loss. That means wasted energy. We have to pay to heat that air, or that heat energy that's lost. And in the summer, it's exactly the reverse. We're cooling this house, it's hot outside, heat energy is going to want to move through this component into the house. So you're going to want to mention about heat transfer and the importance of insulation and how it helps save energy by reducing or eliminating that heat transfer through a building component. Let's go ahead and walk upstairs and take a look at the attic upstairs. Okay, we're going to start with the attic behind this knee wall. So we're going to go ahead and we're going to take a look in here. We see that we have some fiberglass batts in here, roughly 12 inches deep. So the proctor may ask you what R value exists Again, I just turn to my BPI standards. Okay, roughly 12 inches deep. It looks like they're installed pretty good, so we have about an R30 there. But you can see we have areas where insulation is missing. Okay, so we're going to want to recommend that those areas that got forgotten get insulation. We're also going to want to make sure that we align our thermal boundary with our air barrier, which is going to be at this knee wall. So we're going to want to call for air sealing and insulation on the back side of this knee wall. We want to make sure that our thermal boundary and our air barrier is here, and we want to make them align. So we want insulation and air sealing prescribed in this area. We also have an attic hatch that we saw earlier was very leaky, so we're going to want to recommend some gasketing of some sort, or perhaps something like this. A nice gasketed and insulated attic hatch door. And again, the key here is making sure that our thermal barrier and our air barrier are all aligned on the same plane. Okay, so our conditioned area is inside this box, so everything around it we want to air seal and insulate. Let's go ahead and take a look in the main attic. Okay, when you get up into this main attic, you're going to see that it is filled with cellulose, loose fill cellulose. It has depth markers. It's at a depth of 11 inches. So the proctor may ask you, with the existing insulation, what R value do you have? Again, just turn to your BPI standards. The BPI standards show me that loose fill is roughly 3.7 inches, or 3.7 R per inch. Okay, I've got 11 inches up here according to my depth marker. So 3.7 times 11, I have roughly 40 R up here, or R40 worth of insulation in this attic. So this attic is well insulated. You probably wouldn't need to make any other recommendations up here, and because cellulose is a good air barrier, with the cellulose we probably have reasonably good air sealing and we've got a good R value. So you don't need to make any other recommendations for this particular attic. Let's go downstairs to the addition and take a look at that attic. Okay, we're standing in the addition. In the addition we have an attic above us. So we're going to go ahead and get the hatch opened up. Okay, for your BPI field test, you're going to make the assumption that this attic is uninsulated. It actually has fiberglass bats up here that we use for training, but for your BPI field test, the assumption is this attic is uninsulated. So you're going to want to make a recommendation of what should be done up here. First of all, you're going to need to know that you're going to need baffling because we have soffit vents on either side. So we're going to need baffles to help prevent wind washing. The baffles will allow the air that gets through the soffit vent to blow up over the insulation instead of blowing the insulation back away from the ends of the attic. So you'll recommend baffling, and then make a recommendation for insulation. Air sealing, you're going to want to recommend that, and then maybe some good loose fill cellulose or some Infiltration up here, or even bats. Properly installed bats with good air sealing are a good cost-effective option. You'll also want to note that if there were any chimneys or anything up here, you would want to provide baffling to prevent for fire spread. So if you have a chimney chase or a flue, you need baffling around that before you insulate to prevent from any kind of fire. You don't want those hot items next to combustible materials. Okay, a few more things we need to address on the general home inspection. You always want to make recommendations for things like low flow shower heads. Okay, it's an energy saving feature, so we can put on low flow shower heads, faucet aerators, low flow toilets, things of that nature. So we'll want to discuss those with the homeowner. Let's go ahead and finish our general inspection. We have a wood burning fireplace. It's basically a great big hole to the outside. We've got a chimney, it's wide open to the outside, it's a large hole, so it's a big source of energy waste. Stack effect, air in this house will always be moving up out of that, or cold air can move back in. So recommendations may be to completely plug this off. They have a central heating and cooling system. This is not their only source of heat. It's probably only there for looks. Maybe they don't ever use it. So plug it off. Or make a recommendation for a gas insert that's got a nice sealed front on it so we can get rid of that big hole to the outside. Let's go ahead and finish up in here. Okay, we have a refrigerator. So under base load measures, we would mention to them to consider refrigerator replacement. There are metering devices you can put on the fridge that will tell you their energy consumption. And then you can compare that, see where they're at, and make recommendations for new, more energy efficient appliances like refrigerators. Okay, especially old refrigerators, and the new ones are a lot more energy efficient. Another mention you want to make to the homeowner is CFLs, compact fluorescent light bulbs. Okay, anywhere you can use those in the house, there'll be a lot of energy savings. Let's take a look in the mechanical room and see if there's anything in there we can do to help save energy. They already have a nice high efficient heating and cooling system, but they have a standard tanked water heater that has a lot of standby losses, and it's not very efficient. It probably runs between 70–80% efficient. So I'd make a recommendation about perhaps a tankless water heater so you don't have standby losses, or a more energy efficient direct vent water heater. At the very least, insulation on this to help eliminate or reduce the standby losses. And that concludes the general home inspection and the insulation module of the BPI field test. Okay, the next module is the domestic hot water inspection. This is required, and you need to show proficiency at this if you're doing the building analyst field test. This part is not required for the envelope professional. Basically, you're just going to show proficiency at pointing out the domestic hot water, what type it is, some of the controls, some safety devices, and make some recommendations. Now, some of this stuff you've already completed when you did the combustion safety test, so you do not need to come back and do this again, but there's a few things that we missed in the combustion safety test that we need to talk about. So again, you're just going to point out this is a gas-fired domestic hot water heater, it's a tanked water heater, it's a 40-gallon water heater. We've already addressed the venting system and the safety controls when we did our combustion safety check. We just need to make a recommendation to the client that it would be a good idea, and we would recommend that we insulate this tank. Wrapping insulation around the tank will help reduce our standby losses. As this water heater sits here, it just loses heat to the ambient or the air around it. And we'd also make recommendations to insulate the hot water pipes. Any of the hot water lines that are exposed that we can get to, we want to go ahead and recommend that we apply insulation to those. And that's it for the domestic hot water inspection module. Okay, the next module we're going to discuss is the duct sealing module. The duct sealing module only applies if you're doing the envelope professional. It does not apply to the building analyst. Okay? So basically for the duct sealing, we're going to be using a tool called a pressure pen. We use that in conjunction with the DG700 manometer. So to do a pressure pen test, we need to have our blower door running, and again we need to get to -50 pascals, or as close as we can. Okay? So we're running 48, that'll work just fine for our test. So make sure that's running. Go ahead and turn this DG700 on, and we're just after pressure. Okay, so we just turn it on, we're in pressure mode. Just like we did on zonal diagnostics where we hooked a tube to the input port, we hook our pressure pan to that input port. Now, we're going to be testing ductwork, and our biggest concern is any ductwork that's outside of the thermal envelope. So you have to be able to assess the house and go, okay, what ductwork is in and out of the envelope? Well, we know we have a crawl space. We know the crawl space has ductwork in it. So we're going to assess that ductwork first because we know it's outside of the thermal envelope. So let's go check it out. So we have ductwork in this crawl space. We've already been in the crawl space and evaluated it. We knew it was leaky. Okay, we're going to go ahead and put our pressure pan right over the supply register. And we're going to be looking for a reading. And you can see that our number is 27 pascals. Now remember from zonal diagnostics, the closer to 50, the more connected that is to the outside. That tells me that this particular section of ductwork has a very large leak to the outdoors in it. I'm pulling in a lot of outside air. Remember, the closer to 50, the more connected to the outdoors it is. So let's go on the other side of the crawl space and evaluate that supply run. I have another supply run here on the other side of the crawl space. I'm going to put my pressure pan over it. Now you can see on this side, my number is 2 pascals. It's much closer to 0, much lower than the other one. So that tells me that I'm going to prescribe or recommend my duct sealing over on that side of the crawl space. I'm going to focus on those things over there. This is a tool that helps me narrow down and find where should I expend my time and energy to seal ductwork. It's obvious we have much bigger leaks over there. Let's take a look at a few more examples throughout the house. Okay, another area I want to focus on is we have a supply run here, and it's obvious that it runs through this attic behind the knee wall. So I'm going to go ahead and test it because it's outside of the thermal envelope. And again, you can see I have a very large number on there, 30 pascals. The closer to 50, the more connected that is to the outdoors. So again, this gives me a clue, it gives me a direction. I'm going to focus some attention on duct sealing over in this area because I know I've got a large leak to the outdoors here. Okay, let's go upstairs and take one more look at a supply register upstairs. Okay, we have a supply register here in the upstairs. The reason I'm focusing on this one is because this part of the house is a cantilever. It cantilevers out a few feet past the main framing or exterior framing of the house. So this cantilever portion is outside of the thermal envelope, and I have a supply run or a piece of ductwork running right out to it. So I want to check it because I know there's a couple of feet of it that are outside of the thermal envelope. And again, you can see I have a number. It wasn't quite as high as the last ones, but I am getting a number, okay? 13, 14 pascals. So I would want to go ahead and take a look into this and see what we can do to improve that. Now where it's all finished, the cantilevered side is finished, our only option may be to pull the register and look in there and see what's going on. But again, this is a tool to help you determine where your duct leakage is. Then you'll want to make a recommendation to the client on how they should handle that duct leak. What types of materials would you use to seal the ductwork? So you're going to want to recommend things like mastic, fiberglass tape, things of that nature, silicone, whatever, to seal those gaps in the ductwork and do good air sealing. Okay, that concludes the air sealing module of the BPI field test. All right, the last and final module is the test out module. This is for envelope professional only. Basically for the test out module, you just need to mention to the client or the homeowner, or in this case the proctor, the need for blower door testing after you get done with all of the measures, okay? If you've done air sealing and insulating, you want to run a blower door test again and make sure that you've actually achieved something. Have you reduced the leakage in the house? The other important thing to mention is the need for CAS testing. Anytime you change the dynamics of the house or the way the house works, you have to do CAS testing, just like we did in the combustion safety. Because changing the dynamics of the house can change the way that natural draft appliance vents, and you can cause a dangerous condition. And that's the end of all the modules. Some recommendations I would make to you guys. Watch this DVD and pay attention. Take notes. Watch the DVD as many times as you can. You're going to have to go through this test and show all the proficiencies in the areas that we just went through on this DVD. The proctor cannot help you. There are some questions he will ask you that you need to have answers for. And remember, the guidelines. Everything you need is in the guidelines. Okay? It is a timed test. You'll have 2 hours per test to complete it. So if you're doing building analyst and envelope, you'll have 4 hours to complete both of those. Most people do both of those tests in about 2.5 hours time. If you're doing one test, don't panic, don't rush, you've got plenty of time. And remember to refer back to your checklist. Make sure you check it off. The proctor can't give you hints or help you, so you're on your own to make sure you've covered everything, okay? Now you can go through these modules just like we have in the DVD. Go through the first one, go to the second one, so on and so forth. Or you can go through them in whatever flow works best for you, however you're most comfortable. If you want to skip around and do this section first and that section next, whatever works for you, but just make sure you refer to your sheet and check off everything you've done. And if there's anything you missed, you can go, oh, okay, I forgot to do that. Let me go back and do that. That's perfectly fine, okay? Good luck.